Hey folks, I got a question from Connor and I was trying to figure out how to type it out and I thought I'll just make a quick video. This is from the review that you guys have, part from 6.1, where we were dealing with angular speed versus linear speed. And you might remember those two formulas that we had for arc length being the radius times the angle in radian measure. So if we had some arc length and some radius, if if this angle is measured in radians, one of the reasons we use radians, then the relationship between R and S is very straightforward. The radius times the angle is the arc length. A slight modification to this formula that we started to use was velocity, which is really just arc length over time. So instead of being some static arc length s, it's some speed of rotation. Is still related to that radius of the rotation of the circle that you're rotating through, times, instead of theta, that theta is considered to be also moving. So that theta becomes omega, W if you prefer, that radians over time. Excuse me. So our arc length turns from, say, feet to feet per second, and our angle, instead of being radians, becomes radians per second. So they both essentially become speeds instead. So it's still that, essentially just a modification of that same relationship. So if we're talking about linear speed versus angular speed, this is the relationship that we're talking about. So we're told that this DVD player has a rotational speed of 880 RPMs. Now, excuse me, RPMs are not omega, unfortunately, but RPMs are a very common way to have angular speed or rotation speed expressed to us. We need to remember that RPMs does stand for rotations per minute. So we're gonna have to convert that into the unit that we want, which is that omega, and we're specifically told to have it in radians per second. So we've got to turn this rotation into radians and these minutes into seconds. So I'm going to set up a little dimensional analysis here, 880 rotations per 1 minute. That's our RPM in kind of a rate form, a fraction form. We want to get rid of rotations. So I'm going to get rid of rotations and put in radians. Luckily, we know that there's 2 pi radians in every one rotation. While at it, we've got to get rid of this minutes and turn that minutes into seconds. So again, we want the rotations to cancel here. That's why this rotation had to be on the bottom. We want minutes to cancel. So this one's on the bottom, so that one has to be on top. And we know there are 60 seconds in 1 minute. So if we multiply all this together, we're going to get an 880 times a 2 pi divided by a 1 times 1 times 60. And it's radians in seconds. So it's radians per second. And it'd be nice to reduce some of that. So I'm going to cancel those out, cancel that out. Excuse me. And we get a omega, a rotational speed of 88 pi thirds radians per second. So that's this omega, 88 pi over 3, and that's our radians per second. So one of the things to be careful about here is this, changing it, making sure we're changing it from minutes into seconds. That's easy to forget in this problem. So that's our omega, and we could list a decimal approximation here if we wanted to, or if the computer wanted it. You guys know me, I like the exact values. So if the DVD has a radius of 4 centimeters, so if this DVD's radius is 4 centimeters, and this thing is turning at 88 pi over 3 radians per second, we're essentially being asked how fast is the linear speed along the edge. So how fast is this point going along the edge? Or really any point along that edge. How fast is it spinning? This bothers people a little bit that this is a curved arc, but it's called a linear speed. It's not called a linear speed because it's moving in a straight line. It's called a linear speed because it's measuring linear distance. So meters is a linear measure. So meters per second is a linear measure speed. So it doesn't have to be traveling in a straight line for it to be a linear speed. So be a little careful about that. But our relationship up here, this v, our velocity will equal our radius times omega, we have all our pieces, as long as we're careful. This omega, again, is our rotational speed, 88 pi over 3, and again, that's radians per second. This radius, we have to be careful, is not 4. We're asked to give this in meters per second. Meters per second is pretty standard for velocity in metric. So meters per second is a common ask. But this 0.4 or this 4 is in centimeters. So if we want to have this answer be in meters per second, we've got to convert that centimeters into meters. So actually, I want to turn that into 4 100ths. Just going to make my multiplying a little bit easier. So 4 100ths of a meter. Then we're going to get a nice 300 in the denominator, 4 times 88 pi in the numerator. Can do some canceling again here. That 4 is going to cancel. How many 4s are in 300? Or how many, what, 75? Yeah, 75. So 88 75ths times pi, and meters times radians is just meters. Again, that's the lovely thing about radians. So meters per second. So a lot of the danger in this problem comes from these units. You have to be careful about the seconds from the minutes. And we've got to be careful about the centimeters because we're asked meters. So that 88 pi over 75 meters per second, if we're looking for it to be an exact value, which is always beneficial. Always work in exact value. When you get to the end like this, you can now say, okay, do I want a decimal approximation? If you do, take your decimal approximation from this exact value. Approximating along the way, you will compound your error anytime you multiply by it or anytime you modify it. Your error can compound on itself, and particularly when you're talking about angles, that can get to be a pretty big error pretty fast. So I hope that helps. Not only you, Connor, but anybody else who looks at this later. And if there's anything else you need, let me know. Have a good night.